Hello everyone. In this lecture, we will discuss the hypergeometric distribution. Now, in the previous lectures, we have discussed the cases of. In the previous lecture, we have discussed what is a discrete distribution, what is continuous distribution. Under the discrete distribution, we read binomial distribution, Poisson distribution, and one more distribution as we are supposed to discuss is the hypergeometric distribution. So there are certain situations where we need to sample with replacement as well as without replacement. So now this distribution will leads to a hypergeometric distributions, right? So we will see likewise as in the earlier cases, we will see what is the probability function for the hypergeometric distribution. So you consider, suppose a box contains capital N objects, or you say screws or anything, things, out of which M are defective, M number are defective, and N number to be drawn. The objective is to get X number of defective screws in a draw of N numbers out of total N with M number as defective. So there arise two cases. Case 1, it is without replacement. And in without replacement, we know the probability function f of x, right? The probability function f of x is given by the cardinality of the event by the cardinality of the sample space. So here the sample space is your total is n, out of which you draw n in a draw of n items. Out of the total is n and m is defective. We need to get x success. So the probability here is, the sample space is this, and what we choose here, so we need x success, right? Means x defective out of n, out of m defective we need x defective. The objective is to draw n of which x number of defective. So defective is our success here. As we see in binomial distributions. So now x number of defective, so non-defective is associated with it. So total minus m, and the non-defective is total drawn is n and x number is defective, right? So this is given by this, or in other notation I may write it mx. This is just another notation. This is n minus m, n minus x, and this divided by nn, right? That means my ncx is another way it is denoted by this. So this is the probability function. When there is without replacement. Now the case of with replacement. In with replacement, what will happen? Once we draw a thing, we will keep it back, again we draw. So the chances, the success for each trial is same. So it is behave like a special case of special case of binomial distribution. Special case of binomial distribution. Right, here P is my probability of getting a defective screw. Getting a defective screw. So this is, I can say, my probability of my success. So it is given by the defective screw. The probability is given by, it is M defective. The probability of a defective screw is given by, out of n we have M number is defective, right? M out of n. So simultaneously, what is your Q? Your Q is 1 minus P is 1 minus M by n. Now what is the probability function? If you recall the binomial distribution, your fx is equal to ncx, right? Out of n row, we need x success. How many success? X success. At the same time, we have 1 minus M by n failure, right? So here we substitute. It is ncx. P is my M by n to the power x, and Q is my 1 minus M by n to the power n minus x, right? So this is the probability function. Or if I write it in the other notation, this combination, here is M by n to the power x into 1 minus M by n to the power n minus x. So this is the case of your with replacement, right? That means our with replacement is simply the special case of binomial distribution, right? The special case of binomial distribution. So now coming to it is a what type of distribution? In a remark we can say binomial distribution is a the hypergeometric distribution is a discrete distribution. Right, it is a discrete distribution. And if you think of its mean, mu is expectation of x is, if we work it out, summation xi fxi, it will lead you to a result, right? N into M by n. So is it not resemblance to n into p as we studied in binomial distribution, right? So it is in hypergeometric distribution. Likewise, if I ask you what is the variance, the variance sigma square is expectation of x minus mu square. If we work it out, and the variance will be obtained to be small n into capital M, small n minus capital M into small n minus small n, this divided by capital N square into n minus 1, right? So this will be the mean and variance. Just you remember this mean and variance, right? Now in another important remark too, I can say if n, m, n minus m are very large in comparison to your small n, then no matter, right, whether we sample with replacement or without replacement, because n, m and n minus m are very large. Out of this very large amount, if you are not keeping back one item, then certainly it is not going to hamper, right? So in that case the hypergeometric distribution is simply the special case of binomial distribution with the probability function as we discussed under stage 2, case 2. fx is ncx p to the power x means m by n to the power x into q means 1 minus m by n to the power n minus x. So this is my p, is not it? This is my p and this is my q, is not it? So this is my p to the power x, q to the power n minus x, ncx, right? So this binomial distributions, this hypergeometric distributions can be viewed as your normal distributions. So in a large sample, in large population, that means I can say in a large population, population means, as I said, n is very large, and similarly what will happen means this hypergeometric distribution can be viewed as the special case of binomial distribution. Okay, now let us see some examples. So coming to one example, if we draw a sample of two gaskets, means here an is equal to 2. We draw a sample of two gaskets, means here an is equal to 2 we draw, containing 10 gaskets, means capital N is here 10, right? 3 of which are defective, means capital M is equal to here 3, right? Find the probability function. The random variable is the number of defective. So total M number of defective, 3 number of defective, and we are drawing 2, right? So nothing is mentioned, means we will discuss it under two cases. Case 1, it is my with replacement, and case 2, it is my without replacement. For sampling with replacement, it is my case 2 say. So what is the probability function? It is ncx p to the power x. What is here p here? Here p is here m by n, right? P is here m by n, m is here 3, right? And total is my 10. So here mp to the power x, it is p to the power x, and q is 1 minus p, right? So this is the probability function. Once we find this probability function, and here we draw up two gaskets in a box containing 10, 3 of which are defective, right? So we are drawing two gaskets. So getting 0, no gaskets, what will be the probability? We substitute 0 here and calculated to give it this. And similarly drawing one gasket, so we put x is equal to 1 here and it will give it. And for two gaskets, means we are drawing two gaskets, it may be no gasket, one gasket, or two gasket, so putting this here. Now similarly for without replacement, here fx is mcx, right? N minus m c n minus x. For your without replacement case, what is the probability function? mcx n minus m c n minus x divided by ncn, right? So substitute the value m, n, and we get, this is the probability function. Now we have to two gaskets we are choosing, so either no or 1 or 2. So putting x is equal to 0 here, it will give you this 21 by 45. Similarly for putting 1 also it will give this, and putting x is equal to 2 here, right? F of x is equal to 2 here, it will give you this. So this is the answer. Coming to one more example. Now coming to this another example. A test of extrasensory perception consists of naming in any order 3 cards, right? So here n is equal to 3 here, naming 3 cards drawn from a deck of 13 cards, right? Your total number of cards is 13. Find the probability that by chance alone person will correctly name no cards, means f of 0, and 1 card, means f of 1. 2 cards means f of 2, 3 cards means f of 3. So a perception consists of naming any order 3 cards randomly drawn. 3 cards. So of course m is 3 here, right? And we say it is suppose here without replacement, say. Suppose here without replacement, say. Then what is the solution here? The solution is like this. Here capital N is equal to 13, capital M is equal to here 3, small n is equal to here 3. Since it is a case of without replacement, the probability function is, so now the probability function is given by, it is a case of without replacement. So the probability function is this, substituting m n and n, we get this. So simplified to give it this. Now coming to question number A. What is f of 0? If you have substitute 0 here, x is equal to 0 here, it will give you what? 3c0 into 12c3 by 13c3. If you simplify it, it will give you 120 by 286. 120 by 286. Similarly, if I solve the others, then it will give me, this b will give me 135 by 286. 135 by 286. If you solve this c will give me 135 by 286 again. So if you simplify it, putting x is equal to 0, it will give you this. If you similarly put x is equal to 1, it will give you 135 by 286. Putting x is equal to 2, it will give by 30 by 186. Putting x is equal to 3, it will give you 1 by 286, right? Let us solve one more example. Coming to one more example, a cartoon contains 20 fuse, okay? So total number of fuses, capital N, is 20, of which 5 of which are defective. So capital M is 5. Find the probability that if a sample of 3 fuses is chosen, small n is equal to 3, from a cartoon by sampling without replacement, means it is a special case of binomial distribution. X fuse in the sample will be defective, right? So here capital N is 20, capital M is 5, and here small n is 3. So what is here the probability function fx is ncx p to the power x q to the power n minus x. So n is my 3cx, p is my m by n to the power x, and q is my 1 minus m by n to the power x. So this is equal to your 3cx, m by n is 5 by 20 to the power x into 1 minus 5 by 20 to the power, this is n minus x, 3 minus x, okay? So this is 3cx, 1 by 4 to the power x, and it is 3 by 4 to the power 3 minus x. You make it with replacement, okay? You make it with replacement. Then with replacement case is given by this formula. Accordingly, how many fuses are being drawn? 3. So you are asked to find now, what is f of 0 and what is f of 1, what is f of 2 and what is f of 3. So accordingly you find out this. Now coming to one more aspect here is the generating function. The moment generating function we will discuss. The moment generating function is given by, suppose I denote it my g of x, okay? I denote it here my g of x. So my g of x is nothing but expectation of e to the power tx, right? So if it is a case of discrete, summation of xi means e to the power txi into fxi, if it is a discrete case. And if it is a continuous case, then it will be minus infinity to infinity e to the power tx into fx dx, if it is a continuous type. If I want to find the moment generating function of binomial distribution, then the moment generating function is gx is expectation of e to the power tx. So this is equal to summation of x fx. X is equal to 0 to n. And what is your fx now? Summation of x and cx means my x here is e to the power tx, right? This x here is your e to the power tx. So this is e to the power tx and cx p to the power x q to the power n minus x, right? So this and this combined together, summation of p e to the power t whole to the power x, this is ncx q to the power n minus x, right? So is it not your q plus x is equal to 0 to n? So it is this plus this to the power n, p e to the power t plus q whole to the power n, because it is my binomial expansion, a plus b to the power n, is not it? Summation of ncx a to the power x b to the power n minus x, right? So this is the moment generating function for binomial distributions. Likewise, if you ask you the moment generating function for Poisson distribution, the moment generating function is given like this. Here g of t is expectation of e to the power tx. So this is a discrete type. So summation of x means e to the power tx and fx dx, fx. So this is my summation of e to the power tx and fx is e to the power minus mu to the power x by factorial x. So e to the power minus mu being constant taken out, e to the power minus mu summation of, and this combined together, it is e to the power t and mu e to the power t whole to the power x by factorial x. X is equal to 0 to infinity, because binomial is a continuous, is a infinitely many case, means it is the infinite many terms here, limiting case of the binomial distribution. So is it not here e to the power minus mu? It is e to the power this, e to the power mu e to the power t, is not it? So this is the moment generating function for your binomial distribution. The video is getting lengthy, so we close it here. So these are the standard discrete distributions as we discussed. Okay, so we close it here. Thank you.